I've been teaching formal methods and I've been teaching security. I think the big difference is that if you teach security, you have a lot of really funny anecdotes to keep your audience awake. So this was a particularly hilarious bug in Windows Defender, which is the Windows antivirus product. They have something called the MSPNN, which is the Microsoft malware protection engine, which they use as antivirus. There's a JavaScript engine inside, because modern antivirus is not just looking for signatures, but if it comes across pieces of JavaScript it doesn't trust, it will throw them in this execution engine, execute them and see if they do something suspicious, and then think it's malware. And of course there was a bug in there, a type confusion bug, so types will make a comeback towards the end of my talk. So this is something that's enabled on all Windows systems except Windows 9, I think. I'm not really familiar with the different security privileges that you have on a modern Windows operating system, but it's running as anti-authority/system, which is probably not a good thing, as not sandboxed. And you can get at this, via any application that's internet-facing, like a web browser, Exchange, and Outlook. So this is a typical piece of security functionality that was there to protect us, and maybe you were better off turning it off until people at Google actually found this. So one obvious way to, of course, we can use formal methods to get this critical security functionality correct, right? So a typical approach to using formal methods for security is you take a security critical component of a system. So this can be a hypervisor, operating system kernel, or like a TLS implementation, something like that. And then you try to formalize the security guarantees, and you can try to verify them with your favorite formal method. And I think there have been some really nice success stories there, so that's probably familiar in this community, but so there's been the work that started at NICTA on verifying the SEL4 microkernel, which is really impressive. And more recently, there's been a rollout of a new TLS version 1.3, and there's been a lot of work by the people at the Prosecco group in Paris and by Cas Kramer and his team at CISPA on analyzing and verifying this new protocol while it was being designed. So this is sort of the holy grail, right? As formal methods people, we like to see this, that when while you're rolling out a new standard, you're already trying to do the formal verification and analysis. So I think these are really great success stories. And it's sort of classic formal methods, right? So this is what I grew up with in the 1980s. You have a specification and you try to verify it. So I don't want to knock this work. I think it's very important, but I think we should be look wider than this, right? So these things are providing security functionality, and they're sort of obviously security critical, and so that's a reason to look at them. And it's also clear that there are some obvious security properties that we want to verify, right? So they can be hard to specify, like specifying the precise authentication guarantees that you want from a security protocol like TLS is really subtle, but we can do it. But that doesn't mean that if we verify this that we're home dry, because we have to think about all the other software, right? So if you look at the past year, PDF has been an obvious thing that has been attacked. Everybody's using a PDF viewer. Now, if you have a PDF viewer on your machine and you have a verified implementation of TLS running, this is not going to help you, right? So this will make sure that when you download the malicious PDF, it's going through with integrity protection, and it's all secured, so the firewalls don't even see the PDF attachments anymore, right? So this is not going to... So it's not obvious what it means for a PDF viewer to be secure. This is not really doing a security thing. Like, obviously, you don't want it to go around and encrypt all the PDF documents on your hard drive and then act as ransomware. But it's, I would struggle to come up with a formal spec that says that. If you actually, if you look at some of the quotes that vendors of PDF viewers have on their website, so this is an actual quote from Adobe's website. Adobe has enhanced JavaScript so that you can easily integrate this in the level of interactivity in your PDF document. As a security person, I get scared when I see this sort of warnings, right? So actually, there's different versions of JavaScript, and your PDF version viewer might support some or all of them, and of course they might all come back to bite you. So just to run through a few quick approaches that you can use to use formal methods for security. So one way of doing some trying to capture some security properties is with temporal logic or a security automaton. Like where you say, okay, certain action is only possible after I've entered the PIN code. So we'll see that one come back later. Another category of properties is information flow properties, where you do some analysis of the data flow or the information flow through the application to make sure that confidential information doesn't leak, or integrity or untrusted input, which you don't trust the integrity, does not end up like in your program counter. And another thing, if you want to do sort of a more classical horse-style verification, then it's very useful to have a precondition true in all your interfaces, right? So, you know, traditionally with things like Hall logic, we try to prove these kinds of property. If P and we execute S, then Q. So this is for functional correctors. For security, this is typically the thing we're interested in. If not P holds, then we don't want anything bad to happen. And a useful approximation I've found in the past is just to have this precondition. So the precondition true, and we're just going to prove that there are no weird runtime exceptions that might give an indication that something went wrong. But still, these things are not really going to help us, say, write a specification for a PDF viewer. So the specification I would like to write for a PDF viewer would be, this application cannot be hacked. The nice thing about this specification would be that I can reuse it for any application, right? So we know writing specifications is hard. Once you nail down this one, you can apply it to any piece of software. Again, this is a nice idea, but it's really hard to formalize, right? So one of my frustrations in doing formal methods for security is that if you talk to people and you ask them, have a system and you want to verify it, and you say, okay, what do you want to verify? And they say, it has to be secure. And then you ask, now, but what does it mean that it's not secure? And then they say, well, you shouldn't have this attack, you shouldn't have this attack. And that's a bit frustrating. Still, I think the good news in security is that people keep making the same security mistakes, right? So this is on the one hand bad news, but on the good hand it's good news, because it means that we know some of the security flaws that we can look for. So one approach to approximating the specification is taking your a well-known security flaw and trying to come up with some static analysis, verification tool, testing technique to prove that it does not occur, right? So the people of check marks in the corridor, that's basically what they're doing. And there's no shortage of inspirations for well-known security flaws. So I guess you all know the OWASP top 10, which is the top 10 of common security vulnerabilities in web application. So an obvious thing that's lacking here is buffer overflows, because nobody nowadays is stupid enough to write a web application in C or C++. If you think this is not challenging enough, there's the top 25 compiled by Sense. So this is the new version of 2019. And at least there we have buffer overflow back at the top where it belongs. And if you think this is not challenging, you can look at the top 668 of CWE. So CWE is an organization, so it's by Mitre. It's a common weakness enumeration. It's less well known than the CVE. So the idea is they make a catalog of all the security mistakes that you can make. Now it's maybe useful for classification, but if you have 668 of them, this is not. I'm not going to review my code with these 668 weaknesses in mind, right? Although it's useful to have a scroll through them to see if you recognize some of them, and if you have a formal technique that can do anything about them. I think we can do a lot if we just look at the top one. So this is my top one. It's input handling. Most software is secure until you start feeding it input, and if it's input over the internet, then you're screwed, basically, right? And if you actually look to the top 668 of CWE, I didn't do the math, but then you can probably count that sort of half of them are variations of this theme, right? Mishandling input is the most common problem in security. So if we can fix this, I think we're happy. And every year, if there's a new technology, then a few years later you have the name of that technology injection, and there's a new variant where you can cause problem with this thing. Of course, the one which is still prevalent in a lot of, which is really a risk for a lot of companies, is simple word macros. I had a former student of mine who has a pen testing company, and last year they gave a talk at Black Hat in Malaysia, I think, where they discovered that inside, if you look at the bowels in Office, that there's actually another programming language hidden in there, and they explored this and they found out there was a different way to do macros, which sort of bypassed all the antivirus controls. So this keeps coming back. So in the picture, our attacker model is typically somebody over the internet messing with our applications, and then this is typically what they do. They feed malicious input and they make things go wrong. So we have the saying, garbage in, garbage out. I like to say malicious garbage in, security incident out. Or also people phrase this as a malicious garbage in, evil out, right? So, and because this garbage out thing that normally as we accept that this is the case, typically this garbage includes some things that the attacker finds interesting. So here's where LangSec enters the scene. So I think LangSec is a really interesting idea. To look at input problems in a structural way and look at some useful suggestions for do's and don'ts. So this is not my work. This is mainly led by Sergey Bratis and Meredith Patterson. And they gave a talk at the hacker conference, CCC. Anybody here been to CCC? No? Okay. So it's a hacker conference in Hamburg every year around New Year's, where they give a really interesting talk about the science of insecurity. So I should explain the language in language theoretic security does not refer to modeling language or programming language, but it refers to input language. So basically, so some people think that the classical way to prevent input problems is what's called input validation. And some of the entries in the common weakness enumeration will actually say that improper input validation is a potential security flaw, where the idea is you remove some funny characters in your input strings, like backquotes, slashes, which could potentially do damage further on, and you remove them or you encode them, right? This is I think a wrong direction. It can be useful, but you have to be very careful, because one of the problems is that the typical application handles many languages, and if you do input encoding, you're typically thinking of only one of them. Like if you're worried about SQL injection, you want to remove the quotes and the back quotes in your inputs. But if you're worried about cross-site scripting, you have to be worried about pointy brackets. If you're worried about LDAP injection, you have to worry about ampersands and round brackets. So this is sort of a losing battle. So the idea of LangSec is that instead of sort of validating input before you feed it to some really crappy software, you should just make this software more robust and less dangerous. And typically the thing where things go wrong is in the parsing of the input. So this is one of my favorite examples here. So a few years ago, if you disliked people and they had an iPhone, you would send them this text message, because this would crash their iPhone. And the problem here is that you're using 4 different Unicode character sets, and that's more than an iPhone can handle. The funny thing was this was a bug in 2015, and 2 years earlier they had almost identical bug. So my prediction is that next year this will happen again. Now, the input validation approach would be, say, okay, we have a firewall or a web application firewall or your phone application firewall, and your telecom operator or your, an antivirus component on your phone is going to scrape all the incoming test messages and remove dangerous Unicode. But this is probably not the way to go. I think people here also would agree that, if you make software, it should be robust. If it handles Unicode, it should handle it properly, right? So the input validation is not the way to solve these kinds of problems. If you look at the root causes of all these input security flaws, it's typically that a piece of software typically takes a huge variation of input languages, right? So you have a TCP connection, which might be over Ethernet, Wi-Fi, GSM, whatever, 4G, sorry. Maybe you encrypt your internet connection with TLS or OpenVPN or SSH. Then the stuff that comes over there is typically HTTP traffic with HTML5 content, which has a programming language inside it. And you use these other languages, right? So you use URLs, X509 certificates, and the content will include all these strange audio and video formats. And then we have, of course, Word doc, Excel, and PDF documents inside this. Now, as an attacker, this is a really huge attack surface, right? So as an attacker, I only have to find one security flaw anywhere in this protocol stack, and I'm in. And if any of this software is written in C code, then I'm really in as an attacker typically, right? So, and input validation is not going to solve this. We just have to make this software robust. Well, just making it more robust is sort of easier said than done, of course, right? So the root causes that LangSec points at are a lot of these input formats are very ad hoc and informally specified. Sort of if you look at some of these RFCs, it's really amazing how fluffy they are. So there's no surprise that if people implement them, there are ambiguities or bugs. And another thing, if you look at a lot of code, what you actually see is what's coined a shotgun parser. So a lot of applications, they take some network traffic in, then they process a few header bytes, and then they pass this input on further down the protocol stack to be processed further. So you're mixing, you're incrementally parsing bits and pieces of the input, but this also means that your input is penetrating really deep into your application code, where it can then trigger strange behavior, and the strange behavior is then typically called a weird machine in LangSec terminology. So this could be like if you do return-oriented programming, there is sort of weird behavior that you can trigger, and then typically it turns out to be Turing complete, and attacker has to have fun. So how do we prevent this? Well, this should appeal to a formal methods audience, I hope. So we should have precisely defined input languages. We should force people to have regular expressions or grammars to give these input formats. You should then generate parsers. Sort of silly that we have handwritten parser code when, back in the 70s, I'm told they already had parser generation. And then you should completely parse your input, and then further on only start processing with the parsed inputs. And this also means that you should not start substituting strings and then parse the result. You should first do the parsing and then do your substitutions in the parse trees. And this is the way you, of course, get rid of SQL injection and a lot of other injections. And finally, you should try to keep your input language simple and clear, right? But this is hard because at some stage, some companies say that, let's stick JavaScript in there to make it interactive. But so this, if you keep it simple, you have a minimal chance of bugs and ambiguities, and also you don't give a lot of processing power to your enemies, right? So the enemies, they can trigger your parser so they can have fun with it. So the past year, there's been a lot of security updates in PDF. So this is just the harvest for the top scores for the last year. So PDF is a very important attack vector. Like if you do serious penetration testing, you can use like a buffer overflow exploit on a PDF viewer. And you see there were loads of them. And the fundamental reason, of course, is, has anybody here ever looked at the specification of PDF? I feel sorry for you. It's horrendously complicated, right? So there is no way that people can get this correct. And actually, so the CVE, the Common Vulnerability Enumerations, if you actually search their database for like standard file formats, you see piles and piles of bugs. And the more complicated the file format, the more bugs you find, right? So does anybody ever look up the definition of flash? Yeah. So I tried once, I spent one afternoon, and then I found one document on an obscure website which was only 4 pages, so I was suspicious, it can't be this simple. But then these 4 pages are just a list of all the things that you can put into Flash, right? So it's a list of other formats that you can put inside your Flash file. So this was one of this is not my work, so this is work that actually led to some of the ideas behind LangSec. So in the late noughties, people found a lot of security attacks on PKI infrastructure, which is sort of security critical. And it turned out that the X509 specification, anybody look at the X509 specification? Same again. You really have a masochist in the audience, I think. So if you want to do some useful stuff with formal methods, maybe try to formally write down a specification of this, right? So one of the things that can cause problems, and which have caused problems in browsers or TLS connections, is that in a certificate you have a name, but you can have multiple names separated by commas for some reason. and then actually different software will actually either take the first name or the last name. So then if you can get your CA to issue, as mafia.org, maybe I can get my CA to give me this certificate. And other software will think it's a legitimate certificate for PayPal. Then of course they use ANS1. Who has heard about ASN1 here? Right, so these are more people, but it's, yeah, of course you can stick null characters in there and then things go bad. Okay, yeah. I should do spell checking on my slides. And then of course, if you have strings in your certificates, then you have BMP strings, UTF-8 strings, and universal strings. And then you can worry about all these different file formats, and if you can sneak SQL commands in there, and if you can sanitize this. So some of the work that people in my group did was looking at GSM. So if you think that the RFCs and the internet specifications are bad, you should look at the telecom specifications. Anybody here read the GSM specification? Oh, okay, so I didn't actually do this, I had students do this, right? So GSM, they have their own sort of OC-like network layers, and then at the top layer you actually find some things that you might recognize. So you have things like SMS, call control is just phoning, but this is of course obsolete by now. You have cell broadcast, what's it? Yeah, so the broadcast call control, this is like for tsunami warnings. And so we did some work fuzzing this, so very simple mutation fuzzing where you take, so we have a software definable radio setup, so we can generate GSM traffic and then you can just flip bits and bytes in the GSM traffic. So we thought we'd start with something simple, which is SMS. So this is what an SMS looks like according to the specification. So yeah, you think an SMS is simple, but this is what it looks like under the hood. And there's all these length fields, padding, encodings, languages. And then if you start flipping bits, then there's no surprise that you've actually found a lot of security flaws, right? So when we were doing this, yeah, I think sort of half the phones, we could crash them or get very strange behavior. And then some stage we had to, when we were doing the broadcast call control, so the tsunami warnings, we actually had our test set up in a Faraday cage because people in the surrounding buildings were picking up our malicious test messages, even though our test messages said they came, so there's a header byte in there, the teleservice identifier, and I think there's a value that you can use for testing, 99, and phones are supposed to ignore this traffic, but of course they don't, and then they crash. So we only did fuzzing on the phones. We did not fuzz the base stations for obvious legal reasons, but I hope the software is a bit better, but I don't have high hopes, right? Some slogans. This is from the CCC presentation by Sergey and Meredith. So really we want to have, if we have protocol endpoints, we want them to be equivalent so that what you're parsing at one end is the same way you unparsed it at the other end. You want to do full recognition before you start actually touching the code, actually doing processing of the code. And ideally, you don't want your input language to be Turing complete, right? Yeah, so I saw this slide. This is actually the slide that got me hooked on looking into what the hell is LangSec about. But, yeah. So I was doing some work with state machines at the time, which is basically state machine learning, so to get your formal methods for free. And I then realized that there is sort of a link with this LangSec idea. So if you look at a typical protocol, then you will have some input messages, which will have some length fields and some padding. So this is a simple one, like a GSM looks more complicated. But apart from these individual messages and the parsing of these messages, there's also, that you have to do, there's also a notion of a session, where you have a sequence of messages, which we typically specify with message sequence charts. So if you make errors in input handling, you can do this at both levels, so you can get the parsing of the messages wrong, but you can also get something wrong with strange sequences of inputs. And if you look at specs, they typically describe the happy flows of the protocol. Of course, the happy flows of the protocol, they are tested for compliance, and if you don't stick to the happy flow, your software doesn't work. So typically, people will keep tinkering with their software until they have the happy flow right. And then you stop touching it, of course, because something might go wrong. But for security, we're typically interested in the unhappy flows, right? So we try to do funny stuff and see what happens. And so there is this technique of state machine learning, or active learning it's called, where you can just, by talking to a system, you can extract a state machine. And this is a very old technology, goes back to the L-star algorithm from the 1980s. And basically the idea is you just, like if you have a device with some buttons, you just try out different sequences of buttons, and you see what happens. And then you find out, okay, that if I press this button twice, the second time nothing happens. And then you can actually extract a state machine. So we've been using a lot of this to do reverse engineering of security products. So the first thing we looked at was bank cards. So if you have a bank card which has a smart card on there, it typically implements a variant of the EMV protocol, which stands for Europay, MasterCard, Visa. The spec there is only 700 pages. The new contactless specifications is about 2,000 pages. They're public, so you can download them from emvcode.org. Yeah. So actually, at some stage, we sat down and so a PhD student of mine, he formalized the 700 pages in 700 lines of F# at some stage. So you can, there's my suspicion is that people who write these specs are paid per page. So there's no high-level design goals of anything. So we did a fuzzing or a state machine learning of bank cards using LearnLib, which is a tool made by Bernhard Steffen in Dortmund. So it's just sending legal messages to a bank card, but trying out different orders. And then you quickly see a state machine like this. So you get this, it's basically fuzzing, but where fuzzing you try strange messages. We try normal messages, but in strange orders. So within around 20 minutes, 25 minutes, we can extract a state machine like this from your bank card. It's fairly harmless, as long as you only use the correct PIN code, of course, in your test harness. And then you sort of see that there's 1, 2, 3, 4, 5, 6, 7 states here. You see there's a lot of these clouds here, these self loops, which are basically sort of apparently commands which don't affect the state behavior. So if you trim this down for a bit, you get a state machine like this, which doesn't mean anything to you, but then if you know the EMV specs, then you can see if this is actually doing the right thing. So unfortunately, we did not find any bugs. If we'd find bugs here, I would be flying in with my private jets this morning and going home. That didn't work. We found a lot of variety between cars. So Nijmegen, where I live, is close to the German border. So some of our PhD students actually live across the border. So we tested it out with here on the left, you see a German bank card implemented with this Maestro logo. Here you see a Dutch bank card with a Maestro logo. I know that if you stick these bank cards in a Portuguese ATM which has this logo, it will work. There's probably in this state diagram, there's probably the happy flow which really matters, which is identical in both cases. And then there is some superfluous behavior, which is so these things are tested very heavily, but it's only for compliance and not necessarily for security. And of course, you can then also do these security analysis. So actually you have multiple applications on your bank card. This is one of the applications that's actually used for internet banking. Internet banking is offline, so here you see that you can actually see in the state machine that this is the operation to verify the PIN code, and you can see that certain actions are only possible after you've done this. So then another thing we looked at was a token for internet banking. So the banks in the Netherlands, they give you these internet tokens where you stick in your bank card, and then you have these numbers that you have to copy across. So one of the banks had the brilliant idea to use a USB cable to connect this device to your PC. And then you don't have to type these numbers across anymore, which is nice. And then, of course, the only security functionality here of this device is that it will display something, and then the user has to press OK to confirm this transaction. And you have to press OK on this device after you've entered your bank card and after you've entered your PIN code. But actually, of course, this is sometimes the frustration with using formal methods for security. I would like to use formal methods here, but actually, the first time we looked at this protocol, we already saw it was broken, so we didn't need formal methods for that. Because it turns out that if you have a strange sequence of USB sequences, it's actually you can press OK from your laptop rather than from the device, which is sort of the only security functionality that this device has, and they managed to screw it up. But you could find this with state machine learning. So the bank actually had to physically patch these devices because they can't patch them over the air. So yeah, they have to issue new ones if you want one. So this was the old state machine for the flawed device, and this was the new device, which was patched. And I wanted to confirm if we could have found this with formal methods. So we wanted to use state machine learning, but then we needed to press the buttons. So one option would be to hire a bachelor student to press the buttons for us and sit there for a week. But I actually had some students make a Lego robot to press the buttons. So this is our Lego device. So it has two small engines. The engines, maybe for the Lego people in the audience, the engines of a Lego motor, they have the same voltage as the out pins of a Raspberry Pi, so you can hook this up to your Raspberry Pi. So here you see this, this is the Raspberry Pi and some stuff to press the buttons on the reader. And then we were fuzzing the USB interface and then mixing this with, entering the pin code and pressing OK to figure out a state machine. And this is the state machine of the device. I actually fed this state machine to a model checker to see if it was secure because it was getting a bit too big. Now, I would not want my security devices to be so complex, right? And I doubt if anybody sat down and wrote a state machine and implemented it. Because there should basically be two states in this device. Either you pressed OK or you didn't press OK. This was also around the time that the heartbleed attack came in. So then we had looked at TLS. So we did state machine inference for TLS. So this is the protocol state machine of the NS TLS implementation. And here in this thing, we're just basically doing a setup of a TLS connection and then dropping it. And this is sort of what you would expect. So there's like the happy flow here. And if you do anything wrong, you immediately go to the end state. But then if you test OpenSSL, this is the state machine of OpenSSL. This is the state machine of Java SSE. And this was the first state machine where we found a security flaw because you could actually jump from this state to this state. And it means that you actually bypass part of the key exchange, and then you can do the man in the middle attack of this. So the depressing result of this, so we had a Usenix paper on this, is that so all the TLS implementations we analyzed, they had a different state machine. And then typically the older and more venerable the TLS implementation, the messier the state machine, because people have been tinkering with the code for a long time. And two of them had security flaws. And of course then the fundamental question that I have is, so why doesn't the TLS specification include a state machine so that people don't get this right from the start? So in TLS 1.3 there is, after a lot of pushing, I understand behind the scenes, there is now a state machine in the spec in some appendix at the end, so maybe it gets better. So my message here would be that we don't want to see more pro specifications of state machines. We want to have these diagrams in there. And not just on whiteboards and napkins, but actually in the spec. Even if it's in ASCII art. But, so how much time do I have left? Okay, I can do. More recently I've been looking at another category of text and ways to tackle them in a systematic way. So I think there are sort of roughly two types of input flaws. So if I have to separate my top one in 1A and 1B, so one is sort of that you have buggy processing and parsing, right? So the classical example would be that you have a buffer overflow in your PDF viewer, and then you have remote code execution. The second type would be that you have, it's typically called injection attack or a forwarding attack, where the input is sort of forwarded in a few stages to some backend component, which then starts to sort of parse and process this input. Where the classic example is, of course, SQL injection. A more difficult example to tackle is actually cross-site scripting. But of course, word macros are also an example of this, right? So you have some malicious input, it's malformed, but somehow it gets executed. So these are basically, this is in the first case, we have unintended behavior, which is sort of introduced by bugs. In the second case, we have basically intended behavior of the backend, but it's sort of exposed accidentally. So again, in pictures, so the first type of bug would be like a PDF, a buffer overflow in some input format where you just application crashes or starts doing a remote code execution because of a malformed input. In a forwarding flaw, actually the front end of the application is fine, but at some stage it ends up in an API where the malicious payload of the attacker suddenly gets executed. And in a typical system, you have a lot of backends with a lot of different formats, and as an attacker, you can try to create problems with all of these formats. So for processing flaws, I think LangSec has sort of a clear picture of how we can tackle it, right? So you should have a clear language specification and you could generate some parser code. For these forwarding flaws, it's more tricky to tackle them in a systematic way. So of course your backend server should have a properly a robust parser, but because the parsing is not the problem, but the fact that this malicious input ends up in there, and there's sort of two places where you can tackle this. You can do this at the front of your application, and it's typically called input validation or sanitization, or you can do it at the output end. And there's typically a lot of confusion on how to tackle this. And there's a fundamental problem here, because if in the front end we sort of know that it is input, so it should not be trusted, but we don't know yet where this input will end up. And in the second, if we do this at the end of the application, then we know where the input is end up, so we know how to sanitize it, but we don't know which bits are input yet. So I think a standard anti-pattern here is string concatenation. So if you come across string concatenation, it's typically a bad sign. And you notice that sort of, I mentioned that parsing is a big problem. If you concatenate strings, you're basically doing unparsing. So you're creating a potential parsing problem. But I think a more general anti-pattern is the use of strings, right? So in any language, in any flavor that you like them. So strings are of course very useful because they're very generic and you can do anything with them, but it also makes them extremely dangerous, right? So strings are unstructured and unparsed data. So if you move strings around, they might accidentally be parsed in a way that you did not intend. And you see that the same string might end up in lots of different places, and then suddenly it might be used as part of a URL, and then there might be a cross-site scripting attack possible. And finally, what you see is that if an API call takes a string parameter, sometimes there is a really complicated input language associated with this. So the classic example would be here format string attacks, where there is sort of an obscure language feature where they introduce a language which is actually quite expressive and an attacker can exploit. So I grew up doing a lot of type theory, so I think types really can help here. So first of all, you can use types to distinguish the different types of data that you have in your language. So it's silly to use the same type for pieces of HTML, URLs, paths, file names, etc. Because then, first of all, you have structured data, so you don't have to parse it anymore. And there's no ambiguity about intended use of data, right? So if the application is handling like red data and blue data, then you can at least keep track what type of data is and make sure that it only ends up in the right place. So the type confusion bug that was mentioned in the second slide on the malware protection engine of Microsoft is basically having this kind of problem that you could fix with typing. And the second thing is that you can use types to distinguish trust levels. So it's basically the old idea of information flow typing, that you can track the origin of data or control the destination of data through your type system, right? So if I have different people supplying inputs, or if I have some compile time constants that I trust as opposed to user input, then you could use your favorite type system to try to keep these data apart, and then at least you can figure out when there is malicious data entering some API call to a backend, and then you know that at this stage you would have to do some output encoding to prevent problems. So of course you can combine these two levels of types. Actually, and a nice example of this where it's actually used is in the new version of Chrome. So it turns out that cross-site scripting attacks are extremely difficult to root out. If you're familiar with return-oriented programming for C, you can do something similar with JavaScript. So you can exploit bits of JavaScript from libraries to then craft your exploit as an attacker. And the basic problem is that there is inside a web application, you have many different data types. You use strings for many different data types, and so strings are used for URLs, for JavaScript, for HTML, and it's basically impossible to disentangle this mess. So what people at Google have done is that they've replaced their string-based APIs of the DOM with typed APIs, where you have different types for for HTML, URL, and then URLs that you trust to load scripts, and then then you can keep track of which data is flowing around your web application and which data might need to be escaped at some stage. So some conclusions. So if you remember anything about this talk, I hope I've convinced you that security is really about software. So this is where, well, as formal methods people, we know that software is a difficult thing to do or to make. And it's particularly software handling inputs. And so as I try to argue that most of the security problems come down to input handling, and it's either buggy parsing of inputs, buggy state machines, then handling sequences of inputs, or unintended parsing due to these forwarding or injection attacks. And I think it's sort of ironic and it may be a bit embarrassing for us as a formal science community that parsing is probably one of the best understood areas in computer science, and this is where we have all our security problems. So I think also there is something to be done in teaching. So I guess everybody here in their bachelor, they have a course on formal methods where you at least explain people about finite state machines, regular expressions, and context-free grammars. But I think there's still a lot to be done to make sure that people in industry, use these very basic things before they get on to the fancier tools. So I think a LangSec is a nice way forward to tackle some of these input flaws. So to make sure that you have simple, well-specified input languages, and of course, as you would all agree, in a formal language, that you can then generate parser codes to sort of get rid of a lot of these security problems. So my personal additions to this would be the advice to never use strings for anything, and to use the power of type systems to distinguish different types of data that are floating around in applications and the different trust levels, sort of to make sure that you get your validation and escaping right. Okay, so this is my message for today. Thanks for your attention.